the basic definitions that we had seen last time. Okay, so relative motion is the process by which we write the motion of a body or a particle when we from a moving reference frame. Instead of the reference frame being stationary, it is from a moving reference frame. So that situation is called the equations of relative motion or the description of the relative motion. So we started by understanding the relative motion parameters. So far what we had understood is relative position. For example, if we are writing it as R of B comma A, that means we are writing relative position of B with respect to E. So that becomes the individual position of B in the ground frame minus the position of A in the ground frame. And according to that, we had also seen that if B and A are also moving with respect to the ground frame, then the relative displacement of B with respect to A becomes the individual displacement of B in the ground frame minus the individual displacement of A in the ground frame. Okay, so let us start with a quick example to understand this. See, still more people are joining in gradually. Anyhow. So in our particular example here, what is happening is, let's say, in a given two-dimensional frame, ground frame, that is. So with respect to the fixed ground frame, I have one particle B that is present over here at 0,4 and one particle A which is present over here at 3,0. This is the situation at t equal to 0. So A and B are moving with uniform velocities in the fixed xy plane as shown. So if A's velocity is, let us say, 2 cap in meters per second, and B's velocity is j cap in meters per second. And here also the coordinates are given in terms of meters. Then find relative position of B with respect to A at t equal to 0 as shown. Okay. Again, relative position of B with respect to A at t equal to 1 second. And the displacement of B with respect to A from t equal to 0 to t equal to 1 second. So let's start with this question. So it will give us a recap of the concepts that we've learned about relative displacement and relative position. Last time we saw some one-dimensional examples also. This is a nice two-dimensional example to understand this whole situation. Okay, Manav, I'm going through your answer. Yes, the first part is correct. But, okay, first part is correct. Okay, second and third are good. So you can give the relative displacement beta in vector form only. Okay, in I cap, J cap form only you can give.
Okay, sir.
Yes, one your answers are also correct. So see, when it comes to the third partner, relative displacement, now you have two methods of calculating it. One is that you can directly define relative displacement as change in relative position, delta of RB. This is the definition of that. So you can apply that also, because already in first and second part you have calculated the initial and final position. Or you can also use the other formula, that it is the individual displacement of B minus displacement of A, for which also you have the information in the question. So this definition or the formula, whichever, you can use either of the two. So anyway, you can see in the diagram that initially the position of B with respect to A is this vector. And this is the position vector of B with respect to the origin minus the position. So this is our this is our R of B with respect to A, but this is at t equal to 0 in this equation. Okay. So you can see that the first part at t equal to 0. If you want to write very specifically, you can write that position of A is 3 I cap, position of 4 J cap. So position of B with respect to A is becoming the difference of these two vectors. Or you can directly just understand it from the diagram. You don't even need to write in so much detail everything. Okay. So it is minus 3 I cap plus 4 G cap. Now the next thing which is important, that A's displacement in 1 second is going to be how much? Velocity into time. So for the second part, displacement of A is going to be velocity of A into time. And similarly, displacement of B is going to be velocity of B into time. So in general, displacement of A is going to be 2t in time t, and displacement of B is going to be t j cap in time t. Okay. So therefore, after 1 second, position of A will become 3 I cap plus 2 into 1 I cap, so 5 I cap. And similarly, after 1 second, new position of B will become the original position. Okay, so this is becoming the final position. This and this is at t equal to 1 second. T equal to 1 second. So if you want to understand the same thing in terms of the diagram, that geometrically what is happening here, you can see that this is what is happening. A is displacing at the rate of 1 meter per second. So A is reaching here, sorry, 2 meters per second, and B is displacing at 1 meter per second. So A actually displaces by a larger amount than B does, I mean, larger magnitude. So anyhow, so now A should reach here, okay, at 5,0. This is the position of A at t equal to 1. Reach here at 0,5 at t equal to 1 second. whereas the earlier one was this. Okay, so the new position has shifted like this. Okay, so this is at this. So now for the third one, so you have the option. You can either use directly subtract these two, SB minus SA. So you can see that displacement of B was J cap minus the displacement of A, which was 2I cap. So the relative displacement we can write like this, minus 2I cap plus J cap. Or we can also understand it this way, that it is the final position that is at t equal to 1 second minus the initial position. So from these two, you can see that the new relative position that is minus 5I cap plus 5J cap. So this vector has to be subtracted from, or this vector minus plus J. Okay, people. So hope this question is clear to all of you and understood the concept behind it. Okay. So we will see more examples with applications also, but let's first complete the understanding of the various parameters of relative kinematics or relative motion. So we had seen relative position and relative displacement. Now we come to the third parameter, which is relative velocity. So that is, it is the velocity of, let's say, one object, of a moving body or particle, whatever. Let's say B in the frame of, okay, or you can say relative to another moving body or particles. Let's say that one is A. So we write it like this: velocity of B with respect to A. So this is basically what. So now, kinematics, we have seen the definition of velocity. What was the definition of instantaneous velocity in kinematics? It is rate of change of position or rate of change of displacement. Both are equally valid. Okay. So here it becomes rate of change of relative position, or we can say that's the same thing as rate of change of relative displacement. And then we go on to apply the step that what is relative position? It is the position of B in ground frame minus the position of A. So what this becomes? This becomes the rate of change of RB minus the rate of change of RA. When we operate this differentiation, it becomes like this. And by definition, this is nothing but the velocity of B in ground frame. And this is nothing but velocity of A in ground frame. So we have a symmetric kind of definition that relative velocity of B with respect to A is also velocity of B in the ground frame minus velocity of A in the ground frame. This will also go by the same series of steps. SB minus SA. So when we open this bracket, this will become rate of change of B's displacement, which is nothing but velocity of B, minus rate of change of A's displacement. Okay. So ultimately, this becomes the definition of, this becomes the formula for relative velocity. So just make a note of this. We will look at some examples next. Okay, so let's look at a quick example.
Can you scroll up?
Okay.
Done, sir. Thank you.
Okay. So let's say this is the top view of a two-lane road. And what's happening here is that we have long trailer truck, which is moving at a constant velocity of 36 kilometers per hour. And its own length is, let us say, 25 meters. And just at this instant, a car trying to overtake it comes alongside this. So the front of the car is just about alongside the rear of the truck. And the car is trying to overtake it with a constant velocity of 72 kilometers per hour. And the car's own length is 5 meters. Okay. So the car and truck are moving with uniform velocity. Along the straight road as shown. So this is the situation at t equal to 0. So first of all, we have to find the relative velocity of the car with respect to the truck. And the truck with respect to the car. Secondly, we have to find the time t at which the car completes the overtake, or it completely overtakes the truck. So just apply the concept of relative velocity that we've discussed previously and work out the first part from that. So going back to this definition, okay. So velocity of B with respect to A is defined as velocity of B minus velocity of A. So that also implies that, and additionally note down this point, that velocity of A with respect to B is opposite of that. It is minus VB. So like we had seen for relative displacement also, velocity of A with respect to B is an equal and opposite vector. That means equal magnitude but opposite direction compared to velocity of B with respect to A. Yes, very good, Adinath. That's correct. So if we are taking this as a positive x-axis, then what we can do is we can write the velocity of the car as plus 72 kilometers per hour. Okay, so that's the same thing as plus 20 meters per second. And similarly, we can write the velocity of the truck as plus 36. Oh, that's the same thing as plus 10 meters per second. So the velocity of the car with respect to the truck will become plus 10 meters per second, or the velocity of the truck with respect to the car become minus 10. Okay. So this clearly shows us that, if at some point of time while the car is overtaking us, our observer is present in the truck. Observer, it looked like the car is going past at 10 meters per second. Whereas If our observer is present in the car, then to this guy, it will look like the truck is actually moving backwards at 10 meters per second. This is how. So this is what this shows. Yes, very good, Adinath, correct. We will also add one more part to this question. Find the individual displacements. That is in ground frame. At the instant when the overtake is completed.
Sir, can you explain this part again?
Which part?
The from starting.
From starting, the question is pretty clear. You have the truck and the car which are moving parallelly as shown in the diagram with uniform velocities, 36 kilometers per hour and 72 kilometers per hour. So just follow the diagram, you'll understand that. Okay. Now at t equal to 0, their positions is as shown. So the car is just about starting to overtake the truck. So now based on this, we have to find the relative velocity of either the car with respect to the truck or the truck with respect to the car. Okay. And the time when the overtake is complete. So what we have to do here, it's a one-dimensional problem. No? So we write the velocities with just algebraic sign. There's no need of putting the unit vectors. So both are moving in the positive direction, the positive x-axis. So both the velocities, individual velocities are with plus sign, plus 20 and plus 10. Now for the relative velocity, we just apply the formula. Okay. Velocity of car with respect to truck is the velocity of the car minus the velocity of the truck. So this will become 20 minus 10, so plus 10. But this, for example, will become 10 minus 20, so minus 10. Is it clear now?
Yes, sir.
Okay. Yeah, so second part, the time will be 3 seconds. Okay, those of you who sent me the answers, the correct answer is 3 seconds. Okay, let's see how. So there are two ways we can understand this. The whole process of the overtaking, you can understand it either if we are observing from the ground frame. Okay, so we are stationary on the ground. So we observe both the things moving. So we see that, okay, the truck was here and the car was here. And after some time, what should happen is the truck should be somewhere ahead, but the car should be much further ahead so that it has completed the overtake. So this is when the overtake is complete. This time we have to find, but this was the situation at t equal to 0. So the truck is moving with V1 and the car is moving with V2. So what we see here that this position here to this position here, this is the displacement of the car. This is the displacement of the car. Whereas this position here to this position here, you can see that this is the displacement of the truck during that time. Okay, so that's one way to understand it. But a much easier way to understand it is that if you're sitting inside the truck, in the frame of the truck, what is happening? The car was here at t equal to 0. Okay. but it is going past you with a velocity of plus 10. And by the time the overtake is complete, it's reached here. Okay. So this is the separate analysis of it. This is where we are understanding the motion of the car relative to the truck. So the car is moving a total displacement relative to the truck of this much. So this displacement should be how much? It should be 25 plus 5. It should be at 10. So the time should be 3 seconds. Whereas if you understand here, what is happening is that the displacement of the car, this is 20 meters per second. This is 10 meters per second of the truck in the ground frame. This is the motion in ground frame. So the displacement of the truck is velocity of the truck into time. So that is 10t. The displacement of the car is velocity of the car into time. So that is 20t. And what we observe is that the displacement of the car, this whole line, should be equal to the displacement of the truck plus the length of the truck plus the length of the car. So 20t should be equal to 10t plus 25 plus 5. So 20t should be equal to 10t plus 30. So that's giving you the same result, but in a more complicated way. Whereas here it's a more direct way, because one of the things has become stationary for you, so it's always easier to analyze. Okay, but you can also see that through this diagram, I have also calculated the third thing. The third thing part was I wanted to calculate individual displacement of car and individual displacement of truck in this time, so that you got the time as 3 seconds. So you can see the car has traveled 60 meters, whereas the truck would have traveled 30 meters. But to the truck, it will look like the car has traveled only 30 meters. You can also see that the displacement of the car in the truck's frame would also be plus 30 meters. Adinath, the equation you've written, it has to be reversed. Okay, velocity is displacement divided by time, or displacement is velocity into time. Understood? Huh?
Yes, sir.
So just like we have written these equations here, these equations, these are in the ground frame. So like that, in when you look at when this person who's inside the truck is looking at the car, this is the equation. He's looking at the car, but the velocity of the car is not the actual velocity; it is the relative velocity. So the displacement is also not the ground frame displacement; it is the displacement with respect to the truck. You can hope this point is clear. Okay, let's look at our next example. Very similar, but you can say like the opposite situation. Now the two things are moving in opposite direction, and we'll just make it interesting by putting one more object inside. So now imagine the distances are pretty large, so the size of the cars will not matter so much. Cars like particles. So there is one car A and there's one car B. Now A and B are moving in the same lane, so they are moving with constant velocities in the same lane, and C is a car in the opposite lane, so therefore moving in the opposite direction. So this is the situation at t equal to 0. Okay. So A, B, and C are moving with uniform velocities. So this time, let's say velocities are given in meters per second. So A is moving at, let's say, 40 meters per second. B is moving at 30 meters per second. And C on the other side is moving at 20 meters per second. Okay. And initially, these positions are such that the distance between A and B is, let's say, 250 meters, and the distance between B and C at this moment is 350 meters. So treat the size of A, B, and C as negligible. So maybe 1 meter or less in size. So you can neglect that compared to these distances of 250 meters, 350 meters, and all that. Okay. So this is the situation at t equal to 0. So we have to find, first of all, the velocity of A with respect to B, the velocity of A with respect to C, and the velocity of C with respect to B. So these relative velocities we have to find. Then secondly, the time at which A overtakes B, the time at which A crosses C. Okay. And also we have to find where is C with respect to them at this time. So when A is overtaking B, so A and B are more or less at the same position. So with respect to them, where is C? And similarly, where is B with respect to A and C at this point of time, when A and C are crossing each other? Okay. So pretty simple question again, but again you will see that using relative motion makes life very simple. Yes, Manav, that's correct. The relative velocities are correct, which we have sent. For C with respect to B, make sure you're giving with the proper sign also. You know? So just send the answer with the proper sign also for the velocity of C with respect to B. Yes, Vansh correct, Priyam correct, Manav correct. Sorry, Priyam, your answer is not correct. Just check the algebraic sign now, how you are using in the formula. Yeah, I think you have just subtracted the velocities, but without putting the formula properly. So when I write the values of VA, VB, and BC in the above diagram with respect to ground, you will see that the individual velocities of A, B, and C should be like this. This should be plus 40 with sign. Okay. Should be plus 30. But velocity of C should be minus 20. To take care of that. Okay. Or if you take this as your x-axis, as a vector, you should write this as 40 I cap. Write this as 30 I cap. If you're using an I cap, J cap notation, write them like this. You're writing in one dimensional notation also. When you're writing the velocities as vectors, you have to give the proper algebraic sign. Okay. So from this, you can see that the velocity of A with respect to C, when we use this, oh sorry, A with respect to B. So using this formula, you can see that the velocity of A with respect to B is 10 meters per second in the positive direction. Similarly, the velocity of A with respect to C will become 60 meters per second in the positive direction. And the velocity of C with respect to B will become 50 meters per second, but in the negative direction. Yes, very good, Manav. So now it's easier to analyze the time taken and all that from the relative motion point of view. So for example, for this part, you can do like this, that suppose our observer is inside car B. So motion of A and C in B's frame. So how does that look like? So A looks like it's at a distance of 250 meters behind at t equal to 0, but it's coming with a velocity in this direction of 10 meters per second. On the other hand, C at that instant t equal to 0 is at a distance over here of 350 meters, and it is coming with a velocity. So I'm showing the direction with the arrow, so I don't need to put the algebraic sign here. Okay, like this. So when will A be over here? So displacement of A with respect to B should be velocity of A with respect to B into time. Okay. So I want this to be 250, okay, at time t1, let's say, which we calculate. So this should be 10 t1. So t1 is coming to be 25 seconds. And at that point of time, what is the displacement of C with respect to B? It is the velocity of C with respect to B into t. So that will become 50, but with minus sign actually, into 25. It will be minus 750 meters. Okay. So C at that moment is somewhere far away. At t equal to t1, C is reached somewhere here. Which is at 350 meters. Because this should be the displacement. Oh, sorry, much more. 25 into 50, not 30. So 1250. Okay. So this should be 1250. So this one 900 meters here. Exactly, Prem, that's correct. Okay. So I'll just take you to the previous diagram once so that you understand how we have used the sign convention to express the direction of the velocities. Okay. You can use either the sign convention like I've done on the left hand side, or you can use unit vector like I've done on the right hand side. Yes. So whichever you use, okay, ultimately you'll see you will get these lines.
So,
Yes.
sir, can you explain again, like for what you did for where is C with respect to?
हाँ, so where is C ना देखो मैंने क्या किया B के फ्रेम में C का वेलोसिटी देख लिया कितना है, so it's 50 backwards like this.
Yes, sir.
Okay, so I'm sitting in the car B. So initially where I'm seeing C, C is ahead of me in front at 350 meters, but it's coming towards me at 50 meters per second. Okay.
Yes, sir.
Okay, now by the time A is overtaking me, how much time has gone? 25 seconds.
Okay.
So how much B has moved? 50 into 25, that is 1250 meters, but in this direction, in the backward direction. So मेरे respect में मतलब B के respect में C का displacement has become 1250 like this. So where it has gone? It's gone from 350 ahead of me to 990. ठीक है ना? This is clear, I hope.
Yes, sir.
Okay, so this time is 25 seconds and C is 900 meters ahead, you can say, of A and B at that time. Ahead means ahead in its path. As far as A and B is concerned, is behind their path. So in its path, C is now ahead of them by 900 meters. Okay, now same way I want you to calculate the third part. Okay, try to work it out yourself without making any mistake. Yes, Adinath, we can do that, of course. Okay. We can do all this from ground frame point of view also. So that is how you are suggesting that, we can find the position of C and B individually and okay.
Yes, sir.
Okay, so just a second. Okay, so now next thing we want to find when A and C cross each other. So one convenient way to do that is get into A's frame. So if our observer is sitting inside A, then we can see motion of B and C in A's frame. So now this is going to be very interesting because while A is moving, with respect to A, what kind of velocity B is having? B will be having a negative velocity with respect to A. V of B with respect to A. Remember, VB was plus, how much was it? 30, right? Plus 20. 20 and 40, yeah, VB was 30. This one was minus 20. Okay. VA was plus 40 and VC was minus 20. So the relative velocity you can see is minus 10. So I won't put the minus sign here. I've already shown the direction. So the magnitude of the relative velocity is 10. So at t equal to 0 with respect to A, B is over here, 250 meters ahead. And what about C? C is further ahead. Okay. But C is moving with a super fast velocity in comparison of 50 meters per second towards it. Oh, sorry, not 50, but 20 plus 40, so 60. So with proper sign convention, you can see from these, we get V of B with respect to A is minus 10 meters per second, and V of C with respect to A is minus 60 meters per second. So from that radius, okay. So this is also at t equal to 0, and this is at a total distance from here of 250 plus 350. So that is 600 meters. So C will come alongside A at some time t2, let's say, if you want to find out. So displacement of C should be velocity of C with respect to A into time. So when this displacement becomes 600 meters in magnitude with a velocity of 60, the time should be t2. So this should be 10 seconds. Now during that 10 seconds, where has B reached? B has reached somewhere here. This is where B is at time t2. Distance of 150 meters. Now, if you want to put together all this information from the ground frame point of view, that also makes a very interesting thing here. That you will see that, let's say, initially A was here, B was here, and C was somewhere here. This was the situation at t equal to 0. Just like this, let's say. This was moving at 30, moving at 40, moving at 20. This is the situation at t equal to 0. This is 250 meters. This is 350 meters. So we'll see that actually A and C cross each other earlier compared to. So by the time A is reached somewhere here, 10 seconds. So A is reached somewhere here. B is reached somewhere here. C is crossing A. So this is what is happening at t equal to 10 seconds. You can see that B has, at this point of time, B is 150 meters ahead of E. And he is continuing at 40 meters per second. C is continuing at 30 meters per second. And this one is continuing at 20 meters per second. Then after some time, what happens that, so B is somewhere here, A has come alongside. So this is at 25 seconds. And by that time, C has reached way back here somewhere. So this is what is happening in the ground floor. Just a moment. Separate this out. So now if you look at the individual motions on the ground floor, you can see this is a sequence of events. Yes, that's correct. Okay. So the other thing we have to calculate is that at T2, so you also needed to calculate here that at this time, displacement of B with respect to A has become, with a proper sign, minus 100 meters. So B's position is now 250 minus 100, that is 150 meters ahead of A on its path. On A's path, B is, so that also we can see in this diagram, that this is 150 meters. Okay, so I'll minimize this a little so you can go through this carefully. Just make a note of it briefly. Now from this, we will move on to two-dimensional examples of relative motion, where more vector analysis will come into the picture. Here also we have done vectors, but only vectors where they are parallel to each other or opposite to each other. So we just had to use algebra, components or things like that. Next up.
Sure.
Yeah, Shayan, you have asked a very important question, that how do we understand in which reference frame we should solve the problem. So see, the answer to that is, see, if we are looking at the time when B overtakes A, I mean A overtakes B, then we should either be in A's frame or B's frame. C's frame will not be of use to us. And whether we take A's frame or B's frame is one and the same thing. It doesn't matter so much. Similarly, when we want to find out when A and C are crossing each other, either look at C in A's frame or look at A in C's frame. So basically, you're looking at two moving objects. So to understand the motion of one with respect to the other, get into the frame of one of those two. Understood the concept? No?
Yes, sir. Sir,
Ah,
if we found in the C part displacement of B with respect after a cross. Sir, if we found with respect to C.
yes. Yeah. So that one, no? In when A and C are crossing each other, where is B? No? That we found. No? B is this much. No? It's 150 meters ahead of them. See this? No? At 10 seconds, A and C are crossing each other. So where is B located? It's located 150 meters ahead. So this is how we found this. No? That during that time of 0 to 10 seconds, B's displacement with respect to A was minus 100 meters. So initially, where was B located? At plus 250. और उसका displacement minus 100 हो गया. So now what is the new position? It's 250 minus 100. Na? So it's plus 150. That means it's 150 meters ahead of E.
Yes.
Okay, clear?
Yes.
Okay. Now we will see our first example of relative motion in 2D. Okay. So this is a very common example. Vertical rain, or rather you can say rain falls vertically. Rain droplets are falling vertically downwards at a speed of, let's say, 40 meters per second relative to the ground. So now, if a person is in a car moving at 30 meters per second horizontally, find the speed of the rain droplets in the car's frame, that is, and the angle at which the relative velocity is slanted with respect to the vertical. So this is a common everyday experience, that when we are inside a fast moving vehicle particularly, rain appears to be quite slanted, even though the rain might actually be falling vertically because there's no wind present. So if the car were to stop, or if we were to stop, we would observe that the rain is actually falling in straight line path. But because we are moving horizontally at a fast speed, the rain appears to be slanted to us. So that angle of slant also depends on the speed with which we are moving. Not only it depends on the speed of the rain, it also depends on the speed at which we are moving. So we have to calculate this relationship between them. Just try this out. Okay, so people, let's look at the answer for this. Yes, very good. The angle with the vertical will be 37 degrees and the speed will be, so this should be coming out to be 50 meters per second. And the angle with respect to the vertical should be 37 degrees. Okay, so let's see how we can understand this. If the person is in a car that is moving hotly at 30 meters per second and rain is falling vertically at 40 meters per second. So if we take a system of coordinates like this, so velocity of the car we can write as 30 I cap and velocity of the rain we can write as 40 minus j cap or minus 40 j cap. So in this system we can write velocity of the rain with respect to the car will become minus 30 I cap minus 40 j cap. So the magnitude will become 50 meters per second. And now you can see that the direction of such a vector, this is my x and y frame. The direction of such a vector will be like this. This is 30. This is 40. So this angle we want to find out. So you can see that tan theta is equal to 30 by 40 or 3 by 4. So theta is 37 degrees with respect to vertical. So this is, I've used the component algebra method. I will also show you how to use the triangle law method or the geometrical method of solving the vectors. What concept we are using, that we are using this velocity of the rain with respect to the car is velocity of the rain in the ground frame minus velocity of the car. This is the equation that we are solving. Okay, so just work this out quickly once. We go through it quickly once. Let me know if there's any doubt.
Sir,
Yes.
so this 30 is in positive x-axis or negative x-axis?
Hmm.
So this 30, like the speed.
Ah, velocity of the car, no? So I've
Ah,
taken the direction of it to be along positive x-axis, no? So it's 30 I cap.
okay.
Alright, no? So that's why when I subtracted the two, it became minus 30 I cap minus 40 j cap, no? Because it's VR minus VC.
Yes. Okay, sir.
Understood? Yeah? Okay.
Yes. Done, sir.
Yes. Yes, beta, tell.
Done.
This is done now? Okay.
Yes.
Now see, the same thing we can also do by the geometrical method, okay, which I'll show you. So we can see that the velocity of the car is a vector like this. It's a velocity of magnitude 30 meters per second along the positive x-axis. And we also know that the velocity of the rain in the ground frame is like this. It's vertically downward, so it's at 90 degrees to this. So this is the velocity of the rain. So according to the formula, the relative velocity of the rain with respect to the car should be the vector difference of these two, which will be like this. So this is the velocity of the rain with respect to the car, which is the velocity of the rain minus the velocity of the car. So you can see from this diagram that the magnitude of this velocity of the rain with respect to the car is becoming the hypotenuse. So it's 50. And also we wanted to find the angle at which this is inclined with the vertical. So that is the same as this angle. You can see that tan theta is 30 by 40. So theta is 37 degrees with respect to the vertical. So this is the geometrical method of solving the same thing. We're not using the unit vector notation, but we are using the geometrical method. Okay, people. So yeah, if they ask the direction, then this diagram could be applicable. Yes, you can give the direction like this, that it's from the vector, no? This red colored vector, you can show that it's like this, slanted in this way at an angle of 37 degrees to the vertical. Okay. So now we come to the final part of relative motion in terms of the parameters, that is relative acceleration. So acceleration of one moving object in another moving object's frame. So acceleration of B with respect to A, that is the acceleration of a moving body B relative to the frame of another moving body, say A. So now acceleration in kinematics is defined as instantaneous rate of change of velocity. So relative acceleration becomes instantaneous rate of change of the relative velocity of B with respect to. Okay, so it's an instantaneous rate of change with that. And just now we saw that the definition of relative velocity is the velocity of B in ground frame minus the velocity of E in ground frame. So operating this, it becomes rate of change of VB minus rate of change of VA. So it becomes acceleration of B minus acceleration of A. So we get this symmetrical definition here also.
Done, sir.
Yes. Okay, people. Now through this, you can understand something like this: that, for example, if we are inside an elevator which is going up with some acceleration, let's say the acceleration of the elevator is 4 meters per second square. Okay. And acceleration due to gravity is 10 meters per second square. Now, if we are observing an object inside the elevator in free fall, okay. So if an object P inside the elevator is in free fall, what is its relative acceleration with respect to the elevator's frame? Just be careful, okay, because it's a vector difference now. So what is happening is here, if we take our y-axis upwards, okay, so what is the acceleration of the particle or of the object P in the ground minus 10 j cap, because the acceleration of the particle is the acceleration due to gravity with respect to ground, but the acceleration of the elevator itself is plus 4 j cap. So the acceleration of the particle with respect to the elevator will become this, it will become minus 14 j cap. So the particle as seen from the elevator's frame is having an acceleration of 14 meters per second square downwards. Obviously, it will hit the floor of the elevator faster, no, because of its acceleration. If the floor of the elevator had been stationary, then the particle would be approaching it with an acceleration of 10. But now the floor is going up at 4, and the object is falling at 10. So the rate of at which the distance between them is changing is becoming lesser and lesser.
Sir,
Hmm.
so how did that acceleration of particle you wrote minus 10 j?
Because the particle is in free fall, no, beta. So its acceleration is g, no?
हाँ, yeah.
Understood, no? Kinematics of an object in free fall. That's what you mean.
हाँ, sir.
Okay, people. So that's it for today's session. Wish you all the best. Have a nice day. Okay. Next lecture, we'll look at more applications of relative motion. Please try to complete HC Verma's exercise of kinematics by then. And also we'll discuss the doubts of the major test in the next lecture. So have a nice day. That's it for today.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Yeah, bye.
Thank you.
Thank you, sir.